Section 8.3, geometric sequences and series. So I have the notes written already, like as pre-prepared. Before, in the first section, 8.1, we introduced sequences only, sequences, and followed by arithmetic sequences. In 8.2, we introduced series, and then arithmetic series. In this section, we do a sequence series for what we call geometric, the geometric term. So if we have a sequence in this form, 2, 6, 18, 54, if you notice the numbers, I got them by multiplying the previous one by 3. Every time I multiply by 3 to get the following one. So if that 3 is not there and you look at it and say, hey, how do I know multiplying by 3? You can pick any term, divide by the previous term. So you divide 6 by 2 is 3, 18 by 6 is, 3. 18 by 6 is also 3. 54 by 18 is also 3. This number is called the common ratio, R, because it's common among all the terms, and then to find it, we find the ratio of any of the terms divided by the previous. So we call it the common ratio, the common ratio. So if there's a common ratio or such thing like this, there's a pattern in it, that's called geometric sequence, geometric. So in arithmetic sequences, we add the same number every time. In geometric sequences, we multiply by the same number every time. So arithmetic, we add the same number. Geometric, we multiply by the same number. So that's the difference between arithmetic and geometric sequences. Okay, so now let's look at an example, very quick example. an is given 2 times 1/3 to the n minus 1. List the first 4 terms of the sequence. So how are we going to list down the first 4 terms? Okay, so the first 4 terms. Always, if n is not specified, it means n equals 1. It means n equals, or starting at n equals 1. If it is specified, then we just follow whatever specifications we have. Okay, we just follow whatever specifications we have. So in this case, we just have to start with n equals 1. So start with n equals 1, substitute n1. So that gives me a sub 1, which is 2 times 1/3 to 1 minus 1. So 2 times 1/3 to the 0 power. You can simplify further if you like, but I just decided to keep it like so. Then I need to find a sub 2, which gives me 2 times 1/3 to the first power. A sub 3, 2 times 1/3 to the second power. A sub 4, 2 times 1/3 to the third power. So these are the 4 terms, 1, 2, 3, 4. Those are the first 4 terms of the arithmetic, of this series. Notice, what do you notice about these? The reason I did not simplify, because if you want to list them out, like as I did down here in the last line, do you notice the pattern? Every time they multiply by 1/3, 1/3. So 1/3, 1/3, 1/3. Then that gives us a common ratio here, 1/3. That's the pattern here that we see. It's common ratio R to be 1/3. Okay, so here R is equal to 1/3, and so it's called the geometric sequence. Now, if we look at this is called recursive sequence. As we saw something similar to this in the previous section, they give us the first term, a1, and an is written as in terms of its previous term, which is an minus 1. So they told us n starts at 2. So what do we need to find? If I take n equals 2, because n equals 1 already, we know a1. n equals 2, substitute n equals 2 here and there. So that gives me -3 a sub 2 minus 1, or -3 a sub 1. But a sub 1 is 2, it's given 2. So that gives us -6. -6. Now, can I find a sub 3? Yes, all you have to do is substitute n equals 3. And I got a sub 3 equals -3 a sub 3 minus 1. But a sub 2 here, we found it -6, so that gives me 18. You can do the same way and find a sub 4. So far, so we have 4 terms, a1, a2, a3, a4. Now, if I want to list them out, that will look like 2, -6, 18, -54. This is called a geometric series or sequence in this case, with a common ratio of -3. You see, every time they multiply by -3, and usually it comes really from this number, straightforward, negative 3. So the general term for a geometric sequence always is written as an equals a1 r to the n minus 1. N is the number of terms, a1 is the first term, an is the nth term, r is the common ratio. R is the common ratio. So for the previous example, for example, a1 was given 2 and we found out that r is negative 3. So if I substitute them into this box equation or formula, that gives me this 2 times negative 3 to the n minus 1. So this generates all the terms for the sequence for us. So for example, if I want to find a sub 4, all you have to do is substitute n4 on both sides of the equation, and that should give us negative 54. You can try it and see if you get the same result. So how about the sum of a finite geometric series? So in geometric series, unlike arithmetic series, in arithmetic series we had only one formula for the sum. In geometric we're going to have two formulas, one for finite and one for infinite. One for finite and one for infinite. So the finite, this is the finite, a1 times 1 minus r to the n over 1 minus r. That's for the finite geometric series. And r here again, the common ratio, a1 is the first term. Finite means it ends, it stops somewhere. So for example, let's say we are asked to find the sum of this. Find the sum of this. We know a1. We need three things, n, r, and a1. a1 is 1. R is what is r here? What they're multiplying by every time? It's 1/2, right? They are multiplying by 1/2. So we do know a1 and r, but we don't know n. What is n? How do we find n? Well, that's the thing. We're going to learn how to find n from here. So this is a1, this is an, and as I said, r is 1/2. So this 1 over 128, that's the general term of the sequence. Remember, we give you a formula earlier, an equals a1 r to the n minus 1. An here is 1 over 28. a1 is the first term, 1, times r is 1/2 to the n minus 1. So remember, I want to solve for n, so I could use the sum formula. So what is n here? To solve for n, I take that number 128 on the side and prime factorize it. By 2 is 64. If you divide by 2, you get 32. Divide by 2 again, 16. By 2 again, 8. By 2 again, 4. By 2 again is 2. So I can rewrite the 128 as 2 to the 6th power. No, to the 7th power. We have 1, 2, 3, 4, 5, 6, 7 copies. 1 is nothing here, so 1 over 2 to the n minus 1. We can rewrite this as 1 over 2 to the 7th, because 1 to the 7 is 1, and 1/2 to the n minus 1. So we keep it as is. From here, because the bases are the same, these bases are the same, we can set the top equal to each other. So that will tell me that 7 equals n minus 1. From here, n is 8. I found n, but it's not done. Now I need to find the sum. So the sum is a1, 1 minus r to the n over 1 minus r. That's the formula. So the sum is a1 was 1, 1 minus r is 1/2, r is 1/2, n is 8 over 1 minus r is 1/2. The denominator is 1 minus 1/2 to the 8. 1 minus 1/2 is 1/2 in the denominator. And to simplify further on this, you can flip this. That's how it's simplified. 2 times 1 minus 1 over 2 to the 8th power. You can leave it like this. That's totally fine. If you want to simplify the 1/2 to the 8, that's fine too. But this is, it's fine so far up to this point. Let's look at a slightly different kind of example. Find the sum of this using sigma notation or the summation notation from n equals 1 to 20, 3 times 2 to the n minus 1. 2 to the n minus 1. So what do we do for this one? If you don't know where to start, the easiest thing you can think about is to start substituting n equals 1, n equals 2, n equals 3 and see what you get. So if you put n equals 1, you get 3 times 2 to the 0, 3 times 2 to the 1st, all the way to 3 times 2 to the 19th. And then you look at this sum. What do you see here? I see a pattern r equals 2. I see a pattern r equals 2. So now what we need to do here is, it's a geometric sequence, and it's a finite one. It's a finite with a1 is the first term here, which is 3, because 2 to the 0 is 1. That's a 3. 3 times 1, 3. That's the first term. R is 2, as you can see every time they're multiplying by 2. This is an. And n, what is n? From 1 to 20, there's 20 terms. So n would be 20. So again, this is a1, 3, r is 2, and n is 20 terms. From 1 to 20, because we're adding the terms from n equals 1 to 20. 20 cases, 20 terms. So then the sum, this is the sum formula. We substitute in a1, 3, r 2 to the 20th power, because n is 20 over 1 minus 2. Top, nothing can be simplified, but denominator -1. And then this negative, you can just carry it up to give us the answer as -3 times 1 minus 2 to the 20th power. Now, what about an infinite geometric series? Is there a sum for the infinite geometric series? Well, that is based on one condition. We can find a sum for infinite only if there's a restriction R. R must be between -1 and 1. If the value of R falls between -1 and 1, we can find the sum of the infinite geometric series. So the sum, I wrote S sub infinity here for infinite. It's always given by A1, the formula over 1 minus R, and provided R between -1 and 1. So if we need to look at this, 1 plus 1/4 plus 1/16 plus 1 over 64 plus da da da, this means this tells you it's an infinite geometric series. So then we have to use this formula. First, we need to check what is R here, what they are multiplying by every time. They're multiplying by 1/4. R is between -1 and 1, between 1/4. So this is important, because if R is not between -1 and 1, then the sum, there's no sum. We say it diverges in mathematics. It has no sum. Since R, it's checked between -1 and 1, I can find the sum. So I'm going to go ahead and use this formula, A1 over 1 minus R. So A1 is 1, right, over 1 minus R, 1 minus 1/4. And as you can see, the easiest way to simplify something like this is over 1, the 1 on the top over 1. Multiply by 4, all of them, because that's the LCD to all of them. That can clean up all the fractions. So on the top we get 4, and the bottom 4 minus 1. So it's 4/3 or 1 and 1/3. 4/3 or 1 and 1/3. So that would be the sum. So what this means, if you take all these fractions and really add them infinitely many times, the sum will be exactly 1 and 1/3. And how can, you're thinking, how can I find or add up infinitely many fractions? Well, these fractions, if you look at them, 1/4 is smaller than 1, 1/16 smaller than 1/4, and so on and so forth. So these fractions are getting smaller and smaller, and eventually will get closer to almost 0. So that's why you can find the sum. And for those who go to calculus in the future, if you decided to do so, you will see exactly why this works in there. Here in this course, we just learn what it is and how to apply them. Two other examples. We need to find the sum of these two sums. We need to find exactly what each one is. So we're going to do them one at a time. For this one, again, you can substitute I0, I1, but don't I2, and so on and so forth, but not simplify them. Keep them like this. So why don't you simplify them? Because that will tell you what the pattern is. So it is an infinite geometric series with R, the common ratio is 0.1, as you can see. Every time they're multiplying by 0.1. And A1 is 0.1 to the 0 power, which is 1. Anything to the 0 is 1. So then it's an infinite because it goes infinity there. So the sum of the infinite, because R between -1 and 1, it's A1 over 1 minus R. So A1, what's A1? Is 1 over 1 minus R is 0.1. So that's 1 over 0.9. But make sure you simplify this. And how do you simplify this by hand? Multiply top and bottom by 10, because that will give us 10 over 9, or 1 and 1/9. That's the sum. For the other one, here is again 5 times 0.001 to the first power, 5 times 0.001 to the second power, and so on and so forth. Notice it's an infinite geometric series. The common ratio R is always there, multiplying by 0.001, which we can find the sum, which is the first term, that's the first term, A1, over 1 minus R, 0.001. Okay, 0.001. So on the top, if you like to multiply the numbers, you can do so, and that will give us 0.005. And in the denominator, we need to simplify that out. Don't leave it as is. So you can subtract them and get 0.999. So now to simplify this, you can either divide on the calculator or watch how I do it by hand. I have 1, 2, 3 digits, 1, 2, 3 digits. So I'm going to multiply top and bottom by 1,000. So times 1,000. So that gives us 5 over 999, because when you multiply, it moves the decimal points to the right side. And you can leave it like this, it's fine. Or if you write it as in decimal form, it's fine too. Next one, write the geometric series in summation notation. So they give us this one, -1 plus 1/4 minus 1/16, and so on and so forth. So that's an infinite geometric series. It starts with -1, that's A1, the A1, and so A1 here is -1. They're multiplying every time by -1/4, and they told us it's a geometric, and we know that. So we can use the formula AN equals, because what I need to do, I need to find AN to find the sum. N equals, let's say, 1 to infinity. So I need AN. AN, this is the formula for AN that we learned today. Then what we can do, we can substitute these values 1 and 2 in there. So that gives me -1 times -1/4 to the n minus 1. Then you carry all of this and put it inside the sigma notation or summation notation. And that's what we're looking for actually here. Another example, 2 minus 4/3 plus 8/9 minus 16 over 23. So let's see what they're having here. We have A1, again, that's a geometric, it's 2. The R, they're multiplying every time by -2/3. That's what they give us, A1 and R. Every time they're multiplying by the same number. So from A1 and R, I can find A sub n. So A sub n is A1 R to the n minus 1. And just substitute A1 here 2 and the R -2/3. And n has to stay the same. We don't have to find n. Then we just substitute the an inside the sigma notation to get what we're looking for. Last thing to do is to go over some quick true or false questions. So 3 plus 6 plus 12 plus 24 plus da-da-da, it's equal to 3 over 1 minus 2. So this is a geometric series. Every time we multiply by 2, so the sum is A1, as you can see, over 1 minus R. It looks good, but this is false. Because R here, R is 2. Remember, you can only find the sum of infinite geometric series if R is only between -1 and 1. But R is 2 here. So that's why this has no sum, since R is not between -1 and 1. So it's false. So this one is false. What about this one? So this one, it's a finite series, right? Finite series. What happens is the way to do this is to write down the terms. As you can see, I wrote down the terms. That's A1, the first one is the A1, last one is AN, and I have 9 terms, n is 9. I can use the sum of a finite geometric series, which is written in this way, A1 times 1 minus R to the n over 1 minus R. A1 is the first term, the circled part, this part, which is 3 times 0.6, 1.8. So I substitute this in here, I got 1.8 times 1 minus R here is 0.6. And n, there's 9 of them, so I put 9 there, over 1 minus R is 0.06. Does that match the given one? Yes, so this is true. So this is true and the first one was false. That's all we have to cover in this section.